I want to do a couple examples out of the composite function stuff, and then I want to get into the idea of inverses. So that's kind of today's plan. The composite function stuff, guys. Well, I want to deal with that question, or that set of functions up there, and we'll do several different compositions.
I know I'm putting your marker. Yeah,
so if I've got f, let's do it this way. Let's first talk about the domain. If I have the domain of f, okay, domain of f, what is that domain? Or what are my problems? Okay, so x cannot be -5. So I'm not going to write the interval notation right here. We'll write the interval notation maybe when we're done in regards to what these composite domains are. What about g of x? Okay, so its domain is all real numbers, right? Okay. When I write x cannot be -5, the assumption is and it can be everything that I did not write. So if I want to find, let's just do an easy one. Let's go g of x. Okay? Because you can compose a function with itself. And you can do it as many times as you want to. Okay? So all this means is that I'm going to take my innermost function, g of x. And so that notation right there is going to get replaced with that notation, right? Does that make sense? So I get g of 2x minus 5. And now that gives me something maybe that I can actually start to substitute, right? That means that 2x minus 5 is going to be your input inside the function g. So my input is going to be right there, correct? Anywhere I see my x is where I use my input. So I'm going to say this is going to be 2. Okay, now my x becomes 2x minus 5. And then I've got my minus 5. Does that make sense? What I've written here, this structure is the same as that structure, correct? Except for the x now becomes the 2x minus 5. All right with everybody? Okay. I think what might open your eyes maybe to this process. You guys remember back to like 7th grade, 8th grade, when we first started the idea of working with algebra. Before they even introduced variables, they did this. They put a box there, right? Well, that's kind of the same thing here, okay? What should go, when we evaluate g at 2x minus 5, what should go in that box? 2x minus 5, right? Okay? So I think that might help some of us visualize what we're really doing here. If I evaluate that, or simplify that, multiply by 2 through, just give me 4x minus 15. Okay. Is that right? So that is g composed with g. All right. Now I want to talk about what my domain is. What is the final domain for this function? And we have to pay attention to two things here. Obviously, that final thing right there is going to play a role in my domain. Is there any division? And is there any square roots or even roots in there? No. So there's no problem, no new issues that may arise because of the way that new function develops. Okay, so there's all real numbers from that thing. Okay, all real numbers are okay. Okay, so that's the domain from that. But we also have to look at the domain of that first input. Okay, because if there were any restrictions in that first input, then there would have never been an output that goes with it. Does it make sense? That I can run through the function a second time. So if I look at g of x's domain, that was all real numbers, right? So there were no restrictions there for this initial input, meaning that when I input here and get an output, I can then take that output and run through g one more time. So there's no problems at all with this function. Okay? So the domain for 4x minus 15 should be all real numbers. Okay? Now I want to contrast that to a problem that would have some issues at the end. Let's say that we have, let's go G, yeah, so G of f of x. Okay? G of f of x. Coming up with the rule for this, it looks like this. We go G of x over x plus 5, right? Okay? Now I'm going to go to my G function, 2x minus 5, and I'm going to input this object right here inside that box. So it gives me 2, inside the box would be x over x plus 5, and then minus 5, right? Start simplifying this. I get 2x over x plus 5 minus 5 times x plus 5 over x plus 5. Just doing common denominator stuff there. And then that will simplify to, what, 2x minus, let's just kind of do this all at once. Be 2x minus 5x, right? Give me negative 3x. Be negative 5 times positive 5, so negative 25. All over x plus 5. So that's my final composite. That's G composed with f. Okay? What is the issue that shows up? I want to look back to this first. What is the issue that shows up right there? What is the restriction that I'm not allowed to use there? I'm not allowed to use negative 5 there, right? Because it would give me an undefined value. If I essentially asked you this question here, if I said G of f of negative 5, okay, well, what's that mean? It means go to f, plug in negative 5, and see what you get back. What is your output? Well, if I do that, I get negative 5 divided by 0, which is what? Undefined. So I would get undefined right there, which is not a number, right? Okay? How do I then plug that into G? I can't, right? So there's no way I get something kicked back out of G because I really didn't put anything in it. Does that make sense? Okay? Undefined means not a number, okay? It's not that we don't know what it is, it's not a point on the graph. It's not an x value I'm going to use as a point on my graph. So it doesn't have a y value that is accompanying it. So that's why we have to look at this input, and the restrictions that are in that first input need to be restrictions for this domain. So that cannot be negative 5 in that domain at the bottom. Now, we look at that and say, okay, well, is there anything else that shows up? Is there any other restrictions that show up in that final composition? Just negative 5, right? Okay, and that happens sometimes where when you make your new composition, that all you see is the restriction that you started off with as this input, okay, which is fine. But there will also be situations, we'll see this in a moment, there will also be situations where I can't use negative 5, but then maybe as I simplify it, a new value kind of surfaces that I can't use as well, okay? So maybe we'll see something similar to that. I don't know if we'll see exactly that. We'll see something similar to that. Let's go, like we just did, G of f of x, right? Let's flip it. Let's do f of g of x. Okay, so that's going to look like f of 2x minus 5, right? F of 2x minus 5. Okay, so now that essentially means there's a box there, there's a box there, right? We've got to put 2x minus 5 in those spots. So it's going to look like 2x minus 5 over 2x minus 5 plus 5. Okay. Simplify that. 2x minus 5 over 2x. Can the 2x's cancel? Can those cancel? If I were to give you x to be, let's say x is 5. Okay? What's that give me up top? If x is 5. Is it 5? What's it give me on the bottom? 10. Okay? If those were canceled, what would you be left with? Are you left with 1/2? No. Does that kind of make sense why we can't cancel those? All right? Because when I choose an x value before I cancel them, and I get 5 halves, or sorry, 5 tenths or 1 half, I should be able to get the same result when I do cancel it. Okay? So that is not something we can do. We do not have a factor of 1 essentially there. So we can't cancel. So 2x minus 5 over 2x is our final composition. Okay? Now, look at this input and determine the domain of that thing right there. Look at that input. Are there any problems there? Well, we said the domain of this thing was all real numbers, right? This domain x cannot be -5, right? Okay. So I have to keep all the restrictions that come from this initial input. Well, there are no restrictions, so keep nothing. Or keep nothing as a restriction. Come down here. What develops here? Well, x cannot be 0 here. So that restriction needs to be kept, and all the restrictions that may have been listed there need to be kept. So what's the only restriction? 0. So negative infinity up to 0, union 0 up to infinity. And people say, well, there was -5. It could be -5 here. Well, that doesn't matter, okay? Because -5, even though it's in this list, it's not an initial input, okay? Think about, so the idea here, guys, is if I go f of g of 0, okay, why does 0 not work, okay? Plug g of 0 in, okay? Go to g, plug 0 in, you get -5, right? Now, that's saying then, what is f of -5? That's the problem here, right? What was the input that developed that problem? It was 0, right? So 0 cannot work, okay? Now, if I try -5, let's go f of g of -5. Isn't that g function going to transform that -5? So it gives me 2 times -5, -10, minus 5 is -15. So now I'm asking, what is f of -15? Well, that's not a problem. I can do that. I can evaluate that and get an output, okay? So that's the logic of why we've got to pay attention to what our original input domain is, and those restrictions need to be part of our answer. And then when we're done, we get our final composition, we need to look at it and think about the restrictions that are there as well. And we got to make sure we keep both of them, okay? If we, maybe we got some time to do one more here. Just do f of s. Or f composed of s. Okay, so it's going to get kind of messy. But it's going to be f of x over x plus 5, right? Okay. Well, that means that I need to go into f, and everywhere I see x, I need to replace it with x over x plus 5. So the numerator becomes x over x plus 5. So that's that box right there. I need the overall division. And I need x over x plus 5 plus then 5. The hope is that when we've done this, guys, is that result that you get kind of mimics the structure of that first function, right? Does that make sense? So not the first function, but that function. It mimics this structure here, mimics the structure developed right there. But now we got some ugly stuff going on here. Let's go ahead and simplify the bottom. Okay, so it's got to be x plus 5, x plus 5. So the bottom is going to be x plus 5x, so 6x plus 25 over x plus 5. Is everybody okay with that? Okay. The top is going to be x over x plus 5. Okay, now what happens? Okay, multiply by the reciprocal of this thing, right? So it gives me x plus 5 over 6x plus 25, right? What happens there? What's really nice about that? Yeah, those guys cancel, right? It leaves me x over 6x plus 25, correct? That's my composition of f with itself, okay? Now I got to talk about the domain of it. Well, this original input, that thing right there, x cannot be what? -5. So that has to be part of my final domain. X cannot be -5. This is a problem when 6x plus 25 becomes 0, right? So let's see what that looks like. So if I said 6x plus 25 cannot be 0, so give me what, -25, 6? X cannot be that. Okay? So those are my two values that I got to kind of kick out, right? Now, -25, 6, is that to the left of -5 or is it to the right of -5? -25 divided by 6. To the right. Okay, so we're going to go -infinity to -5, union -5 to -26 union -26 to infinity. And those then would be the values that you're allowed to use for f composed with f. All right. My argument here, and the reason I want you guys to see this, is that those. Man. Okay. You did. So 25, 6 instead of 26, 6. I'm sorry. But it's still in the right order, correct? Okay. So flip that, right? Yeah. The reason I want you to see this is because when I did the first domain of f and the first domain of g, we saw real numbers and x cannot be 5. I don't want you to look at those two domains and think those are the only things that are going to be problematic for my composition. New restrictions might develop. Does that make sense? Okay. And my fear is that we get in a habit, just because of the way they're presented. It happens regardless of whether you're using the online platform of WebAssign or use a textbook. You go through a couple examples and you see, okay, every time I do it, the composition is just the domain of either F or G. And you get a habit of seeing that 3, 4, 5 times. Well, that's always going to happen. Well, it doesn't. Okay? So I don't want you to get false impression about what the composition domain is based off of maybe a couple examples that you've seen. All right? So that's always something you got to do, always got to think about. And that's something I think we're fighting, guys. I think a lot of us are, you know, and I don't think it's your fault. I think it's the way that the high school mathematics, just mathematics in general, is structured, is that we are fighting the thought process. Okay, we just want to do. Okay, and if we're not thinking about what we're doing, think about this just in general. If you're not thinking about what you're doing, you're probably going to end up in jail someday, right? Okay, so mathematically, it's the same thing. You're going to end up in a predicament at some point if you're just doing. All right, you got to think about what your concepts, how they're interrelated, and what they're producing for you. Okay. I want to talk about what we call one-to-one functions a little bit. Okay. So this is section 2.8. We'll get about halfway through this, and let's pick up on the algebraic or the analytic aspect of it on Monday. But today is just kind of the logic or the explanation of the concept. Okay. So one-to-one functions. All right. Well, let's talk about inverses first. You guys know inverses of operations, right? If I say addition, what's its inverse? Subtraction, right? It's just what undoes it. Okay. If I say multiplication, you tell me the inverse is division. Okay. And the idea is, okay, if I start with 2 times 5 and I get 10, right? Take 10, divide it by 5. What do I get back with? 2. What I started with is what I returned after I did multiplication and then followed up by the same division. Okay? Same thing happens with addition, same thing happens with subtraction. Okay? You know those inverses. Okay? Well, if we think about it, all our other operations throughout mathematics, like squaring, cubing, that kind of stuff, square rooting, it's just collections of either multiplication and addition, subtraction, that kind of stuff. Okay? So think about the squaring, it's just multiplying twice, right? Okay? So if addition and subtraction are inverses, multiplication, division are inverses, we probably have functions that are inverses of one another. Okay? Functions that act on an input value. So let's word it this way. We have two functions, we have two machines. Okay? The idea is, give you a graphical concept. I start with an input value. Okay? I'm going to run it through a first machine. Let's just call that F. Gives me an output. Okay? I take that output and it becomes an input for our second machine. Does that make sense to everybody? Okay? So an input running through S, we now refer to that as the output of F. Sorry, the output of F, right? It now is the input for G, and it should give me a final output, right? Okay? If that final output, if that number right there matches that number right there, those two machines just undid one another. Does that make sense? Okay? Those two machines, then F and G, are referred to as inverses. And we talked about yesterday, I think I used the potato idea. Okay? Think about this. If I had two food processors, okay, food processor F, food processor G up there on the board. If I take an apple as my input and run it through food processor F, what does it give me? Which would be called applesauce, right? Okay? Take that applesauce, run it through a second machine G, okay? If that second machine G takes that applesauce, puts it back together, and gives me an apple, those two machines would be inverses, right? Does that make sense? Okay? So it doesn't happen, right? If you can do that, if you can reassemble matter like that, you're going to be a very wealthy person, correct? Okay? Kind of like me after this evening. I'm winning $900 million tonight, folks. You'll never see me again. Lottery's at $900 million tonight. I'm winning it. I got the inside track. One by one ticket.
Did you have some problems, like, did you hear the guy?
Yeah, I've just been willing it. Yeah.
Just a random answer. Whatever my dad is, I'm not.
There's actually a guy, and you guys hear about the guy that won $2 million at the Clark Station the other day? Yeah. He went to school here. I'm going to blow him out of the water. I'm going to win 90 times that tonight.
Not really.
Yeah, it's 40. I think take home 400. Take months. No, you'll never see me. I'm going to go buy an island and never do anything else again. All right, so inverses, these are machines that undo each other. Okay, think about this. Let's say that we have F being x squared and G being square root of x. We talked algebraically how they undo each other, don't they? Okay? If I've got something squared, or sorry, some square root in an equation, don't we go through the process analytically of squaring both sides to get that thing to kind of disappear? So give me a number for my first input here. Okay, 7. Run that through my first function. Run 7 through x squared. What do you get? You get 49, right? Now take 49 as the input for G. What do you get to take 49 to run through radical x? 7, right? Does that input match the final output? Yeah. So for 7, it tells me if those two things are inverse. Now, what we have to do is think about what we said in geometry. If we're going to prove something, if we're going to prove these two functions are inverses, it has to be done for every single situation. I cannot find a counterexample. Does that make sense? So that's not enough to say, these two things are inverses. I'd have to try it with 8. I'd have to try it with 9. I'd have to try it with 10. I'd have to try it with every value in between 8 and 9. Every value between 9 and 10. I'd have to try everything, okay? Give me another number that maybe wouldn't work here. Okay, I'll give you one. -7. -7 squared, what's that give you? 49. Run 49 through radical x. What's it give you? 7. Does the original input match the final output? No. Okay? But we've always been taught that x squared and radical x are inverses, right? They undo each other. Well, they only undo each other for a certain series of values, a certain set of values. And they are the values for which x squared is the hard or only number is greater than or equal to 0. Okay? If I do that, then I have two things that are inverses. Okay? Just basically saying we're not going to check, we're not going to use the negative values because that relationship does not occur then. We do not see that the original input matches the final output. That's the concept about what we're talking about with inverses. A lot of functions have inverses, a lot of functions don't have inverses. Okay? And this is something that, as we're working with functions, we're continually trying to figure out certain relationships, certain characteristics that a particular function might have, and it allows us to kind of analyze it and differentiate it differently than other functions, or use it maybe differently than other functions. That brings us into the concept of what a one-to-one function is. Okay? One-to-one function. Let me put up the definition for you. I think the definition is kind of cruddy to think about, but we'll try to muddle through it. Okay? It's a function with a domain A is called one-to-one if no two elements of A have the same image. Okay? No two elements of A have the same image. Now this is of a function. Okay? So kind of discuss that here in a moment. This is a y value, right? For some x1. This is a y value for some x2. What's that saying? The y values of two x values cannot be what? They cannot be the same. So if we think about really what this is saying, it's saying a function that is one-to-one will never have y values repeating across all its x's that it used. Okay? A phrase that you'll see a lot of times after they write this is that they'll say every y value or f of x value has or is paired with one and only one x value. I can't spell value. Every y value is paired with one and only one x value. That's what it means to be one-to-one. And really, the idea that one-to-one means, because it's a function already, and the definition of function says every x value is paired with what? One y value. And only one y value, right? So when we talk about functions that are one-to-one, it's twofold. It's the fact that every x is paired with one and only one y value, and every y value is paired with one and only one x value. Okay, this blue phrase here is what they're saying algebraically there. Okay, no two y values are ever equal when your x values are unequal, when your x values are different. Okay, when that happens, the function is referred to as being one-to-one. What is nice about one-to-one is that we can see it in a couple different kind of visual representations. Think about this one. These are both functions. So let me, it's what we call a mapping. Okay. I think they call it an arrow diagram in this textbook. A lot of times they call it mapping. But does this provide me the order pair 4, 10, 3, 7, 2, 4, and 1, 2? Is you heard that? And we say that's a function because every single x value is only paired with one y value, right? If I see 4 as an x value is never paired with anything else other than 10, right? 3 as an x value is never paired with anything else other than 7. 2 is never paired with anything else other than 4. And 1 is never paired with anything else other than 2 for those x's and y's. Okay? So that's a function. Okay? That function is also what we call one-to-one because reverse it. Start with your y value. Is 10 ever paired with any other x value other than 4? No. Is 7 ever paired with any other x value other than 3? No. Okay? So that is one-to-one. We can go through the other two order pairs and see the same thing. If we look at this one, we get the order pair 4, 10, the order pair 3, 4, 2, 4, and 1, 2. Okay? So that one, still a function, because if I look at the x value of 4, only paired with 10, right? Never shows up again as an x value paired with another y value. So 4 is only ever with 10. 3 is only ever with a y value of 4, correct? 2 is only ever with a y value of 4. And 1 is only ever with the y value of 2. So y values never, x values never get paired up. The same x value never gets paired up with 2 y values. Essentially meaning that passes the vertical line test, right? If you plotted those, you would pass the vertical line test. But now if I reverse it, is 10 ever paired up with another x value other than 4? No. If I look at, let's just go to 2 real quick. Is 2 ever paired up with any x value other than 1? No, 2 is always going to go with 1, right? The y value of 2 always gets paired with an x value of 1. But if I look at these two, is the y value of 4, if I say everybody look at the x that goes with the y value of 4, are we all going to be all looking at the same value, or someone's going to be looking at 3 and someone's going to be looking at 2? Does that make sense? That's the problem. That's why this thing is not one-to-one. Because I cannot tell you, everybody look at the x value that goes with 4, and we all be on the same page and have the same number in our mind. Okay? So if 4 gets paired with an x of 3, 4 also gets paired with an x of 2. This is not one-to-one. This violates the fact, because this is x1, right? This is x2, right? Okay? That's the idea. Because 3 is different than 2. So we say x1 does not equal x2. That's what the last slide said, right? X1, whenever x1 does not equal x2. To be one-to-one, then, f of x1 cannot equal f of x2. So the y value of x1 cannot be the same as the y value of x2 if the function's one-to-one. But what are we seeing here? The y values are. They are equal, aren't they? That's an equal sign. It's terrible. But that violates the definition of one-to-one. Why do we need this? Why do we need the definition of one-to-one? It's because it will tell us what functions have inverses. Okay? Think about this. I told you x squared. When we want to think about its inverse, we have problems with this, right? And the reason we have problems with this, if I put in the line y equals 2, okay? What that does for me is it creates 2 points. The point, oh, I don't want to go 2. I want to go, sorry, y equals 4. What that does is gives me 2 comma 4, that, come on, 2 comma 4, that point, and gives me negative 2 comma 4, right? When I put a horizontal line in there, does that show you that when your x values are different, 2 and negative 2, here it shows me my y values are the same thing, and this shows me that I have violated the one-to-one aspect, right? So what kind of line is that? A black line is a horizontal line, right? So a horizontal line will allow us to check whether a function is one-to-one. Vertical line tells me it's a function, right? Vertical line test tells me it's a function. Horizontal line test tells me whether it's one-to-one or not. Does that make sense? Okay. And the idea, guys, is this. If we're going to have inverses, okay, if I'm going to have an inverse, if that thing is going to have an inverse, then the inverse needs to be a function. Does that make sense? Okay. Well, this is what happens. If I want to look at that thing right there, and I collectively create that thing right there, that's actually going to be what we look at here in a moment to determine the inverse of this function. Is that black curve a function? No. Okay? So that's because that fails the vertical line test, right? So if a function is going to have an inverse, that inverse is going to have to be a function too. So that's the reason, kind of logically, why we have a problem with x squared, or the entire thing x squared in regards to having an inverse. So the horizontal line test, okay, and you pass the horizontal line test or you fail it the same way you pass or fail the vertical line test. If you intersect 2 times, your horizontal line intersects 2 times on your graph. It is telling you that for different x values, you have the same y value, and that breaks the one-to-one definition. Okay? Like I said, why is that important? One-to-one functions are the only functions that can have inverses, or that do have inverses. Okay? Because the idea, if I give you, let's say that I give you 2, run that through f, okay? Get an output, run that through G, that 2 right there should match up to that one, right? That makes sense? Okay? Well, the idea is that these, if they're inverses, I can start with running through G and then run through F and get the 2 here, right? Well, if I do that with x squared and radical x, we're seeing that sometimes I might start with -2 and get out 2, or I might start with 2 and get out -2. Does that make sense? There might be an x value, my original input, that doesn't match up to that final output. If they're one-to-one, that's not going to happen. Okay? If they're one-to-one, it says that output is going to equal that original input in the inverses. But then when I run that same set of information, I use that as the input here, it's going to match that output exactly. There's no question whether it can be positive or negative or something like that. Okay? The definition of an inverse ultimately says that if 2 functions are inverses, the domain and range of function f are a and b. Then when I talk about f inverse, its domain and range become b and a, respectively. So they flip-flop. Does that make sense? We saw this in geometry. We talked about reflections in geometry across the line y equals x. I'll give you this phrase here, and maybe a little bit more of a friendly version, I guess. If A, comma B is in f of x, I'll just say in f, is on f, then B, comma A is in f inverse, where A and B are just your coordinates, just an order pair. Okay, so 2 comma 3, if 2 comma 3 is in f, so at an input of 2, give me an output of 3 in f, right? Then in f inverse, I'm going to have, using the input of 3, will give me an output of 2. See how the domains and ranges just flip-flop? Okay? That's what they're saying there in that blue box. Your domains and ranges, your x's and y's, they just change order. Okay? But the horizontal line test tells me if that happens. Okay? So when we deal with, do a specific scenario here. Let's continue using the one we've been using, x squared. So if f of x equals x squared. Okay? Obviously that thing fails the horizontal line test. It's a function, but it doesn't have an inverse. So what we do is say, all right, well, what values of x does it have an inverse? And they're the values that are greater than or equal to 0. Because now if I put a horizontal line in there, does that horizontal line, does it always intersect? When it does intersect, does it always do it once? Okay, so that thing's going to have an inverse. The inverse of that is the square root of x. It's g. Okay, that makes sense? Okay. So the idea then, think about this. If I go f of g of x, f of g of x, okay? My input is x, right? My input is x, and then I run that through my inverse. These two things are inverses. My original input is x. If they're inverses, what should I get out if my input is x? I should get out an output that is x as well, right? And that's what this is. That's giving me x. Okay? Well, I should be able to reverse it too. I should be able to go g of f of x. This input is my original input. Run it through x. Okay? And then run it through its inverse. It should undo it and give me that thing there. Now, GeoGebra is doing some stuff that's conditional here. But it's giving me, if we graph it, is it giving me that x, y equals x every single time? Okay. So here's the idea. Why does it give me that x? It's because every time that we deal with inverses, they are reflections of one another across the line y equals x. Okay. If I put the point, let's go, give me an easy one, 4, comma 2. That's on that curve right there, right? So what should be on the inverse? What should be on the orange curve? 2, 4. Isn't it? Okay. The idea is if I take any point that is on this orange curve and reflect that point, all right, so C and C prime. C prime's on the square root, C is on the squared function. If I make it a reflection, are we seeing that no matter where those points C and C prime are the ordered pairs, is this one A comma B and this one B comma A? Do they flip? Okay. And that's something that we're very interested in, okay? The reflection, how they function across the line y equals x, will give you the graph of its inverse. And we use that property, and it'll be a while. It'll be like chapter 4 or 5. You guys ever graph logarithms? And logarithms are kind of a pain in the butt to graph, okay? But the principle is that, okay, a logarithm, anybody know what the inverse of a logarithm is? What did you deal with when you dealt with logarithms in Algebra 1 or Algebra 2? Logarithms are just what? What do they define them as? Exponents, okay? So a logarithmic function and an exponential function are inverse, okay? So graphing a logarithm is very hard. But if we understand that it is relatable to its inverse, graphing its exponential inverse is easy. To graph its exponential inverse, graph line y equals x, reflect it, and now you have the graph of the logarithm. Does that make sense? That's one of the techniques that we'll use quite a bit when we graph logs. This is does everybody understand the one-to-one aspect, the horizontal line test? Determines whether it's one-to-one, and if it is one-to-one, it's going to have an inverse. And if they are inverses, they're reflection across line y equals x. And if that is happening, then if A comma B is on one of the graphs, B comma A is on the other. That's kind of the whole summary of what we're trying to get at here today. On Monday, I'll show you how you can algebraically determined. I gave you two functions like x squared and radical x. How can you algebraically go through and prove that they are indeed inverses? And it uses our composition concept. Okay, and I kind of showed it to you when I did f of g of x and g of f of x in GeoGebra, and it gave us back x. But we'll talk about that on Monday. That might free up a little bit of time to tie up any loose ends that you may have questions about towards the end of that class on Monday. But I have given you in your email the key to that practice exam. Some people have been asking, well, what do I need to get on that, get this grade in this course for this 9 weeks? I'll put together an Excel spreadsheet and email that out to you so you can kind of mess around with that and see where you're sitting. Yeah, so I'll try to do that here in the next couple hours. Yeah, the review, if you tally the points on that review, I don't know what it goes out to, maybe like 87 or it might be 100 or something like that, or 105. The actual exam is going to be 95 points. Yeah, so that's, but there, I mean, it's only off by like 10 points, so it's like 1 point per question. That's really the variance, so you don't have to worry too much about it. But they do have that exam. Practice exam does have the question totals on. You can kind of assume that those are going to be similar by 1 or plus or minus a point on Tuesday.